Hi all, my name is Caroline Miller. I'm a senior at Fort Defiance High School and Shenandoah Valley Governor School, and I did my project on maximizing thermophotovoltaic cell efficiency. My project began in the fall of 2019 when I was tasked with developing a presentation on a topic relating to solar energy. I decided to address one of the leading questions that I'd had for years. Why do solar panels have a flat surface? As I began to scour the internet for answers, I quickly realized that I wanted to perform an experiment of my own. I hypothesized that by increasing the surface area of a solar panel, its heat production would increase as well. While I thought that a textured surface would generate more heat, I didn't yet know at the time whether that was a benefit or a setback. I had no knowledge of any solar cells that could utilize heat in order to produce electricity, so that's where I began my research. I quickly discovered that, yes, there are solar panels that utilize heat, and they're called thermophotovoltaic cells, otherwise known as TPV cells. TPV panels differ from normal silicon PV panels in that they're able to utilize heat that would normally decrease efficiency in PV cells. Although both types of solar panels have significant differences, they share common components that allow them to function, such as p-n junctions and band gaps. The cause of the electrical field within solar cells is due to the p-n junction, which utilizes two different types of semiconductor materials that you can see in the diagram on your left, the p-type and the n-type, to give the emitter its negative charge and the absorber its positive one. When an electrical circuit is made between them, current can flow. As for the band gap, it refers to the energy difference that's present between the top of the valence band and the bottom of the conduction band, which you can also see in the diagram on your left. In order for electrons to jump the valence band to the conduction band, they have to receive energy from a particle, usually a photon, that's greater than or equal to the band gap energy. The diagram on your right gives you a more simplistic view of where this process occurs in the PV cell. PV cells use photons with wavelengths, commonly found in the visible light spectrum, to excite their electrons and produce electricity. TPV cells, however, use infrared radiation, photons with shorter wavelengths, to do the same thing. The downside to both types of solar cells is that they experience optical losses, which you can see in the diagram on your right. The goal of my experiment was to determine if a textured surface could minimize those losses and maximize efficiency. Growing up in a small rural town such as Fort Defiance, I didn't have access to the most advanced technology. I planned to use AutoCAD software to design the prototype, but the RAM capacity of the computers that I had access to didn't follow my same train of thought. I ended up using Tinkercad, which meant that I had a few elementary shapes to use, and hey, they were certainly better than nothing. I designed the base on the left so that the panel, the components of which you can see on the right, would attach to it at a 38-degree angle. This texture at the top of the panel was semicircular, the one below it was octagonal pyramidal, and the lowest one was the flat plane, my control group. After many attempts to successfully print the plastic prototype, I began my experiment. My methods and materials were basic. I used a temperature gun to collect data every 30 seconds for each surface type. I did this for a total of 2 hours. First, 1 hour under a 14-watt LED bulb, and then 1 hour under the sun. I entered each of the approximately 720 data points into Excel and graphed the results. On the left, you can see that there was a minuscule difference in temperature between the surfaces when they were tested under artificial light. The difference between the octagonal pyramidal surface and the flat surface was only an average of 0.69 degrees Celsius. However, if you look at the graph on your right, you'll note that the difference increased to 2.09 degrees Celsius when the prototype was tested under the sun. This graph illustrates the ability of both the octagonal pyramidal and the semicircular surface to read at a higher temperature than the flat surface, but only in certain conditions. The data you see here was collected for 1 hour under the sun, and as clouds rolled in and the sun began to set, the temperature difference between all three surface types began to decrease. This trend was interesting to say the least, and if I'd had more time, I would have performed more trials under similar conditions to determine why it occurred. This would come to be one of the many questions that I was left with after my experiment, and it's part of what made me want to keep researching solar energy after TSS concluded. Based on the data shown in the previous graphs, I concluded that my hypothesis was supported. The textured surfaces did generate more heat than the flat surface. However, I began to wonder if the texture may be more efficient in the absorber and emitter. because that's where I thought the most optical losses occurred. This, of course, was an unfounded assumption, and it provoked even more questions, such as where do the most optical losses occur in the solar panel? Does this location differ between PV and TPV cells? And because the absorber and emitter must withstand temperatures of 1026 degrees Celsius, would the increased heat due to the texture be too much for the cells to handle? The questions that I had after my experiment were pushed back on the back burner during the fall of 2019, which was largely due to midterm exams and the bundle of stress that is high school. However, these questions would continue to resurface as I began my internship with Secure Features. My internship spanned from January of 2020 to the beginning of this school year, and during that time, I gained a lot of valuable experience on multiple fronts. I helped review the upcoming TSS program plans as a student who had experienced it firsthand, which allowed me to see both sides of the narrative. I also assisted with the development of a grant application that was aimed at helping students like me access technology that was not available in our rural areas, which will hopefully open the door for students to better participate in TSS as they work virtually. Although I was able to participate in many activities and learn various skills throughout my internship, my favorite project was, by far, the perovskite research paper. I took every question generated from my thermophotovoltaics experiment and chipped away at each concept, discovering different types of solar cells that I didn't even know existed. One of those was the perovskite solar cell, which utilizes perovskites, minerals that have properties such as conductivity and magnetism, which is due to their unique structure. I dove into the research conducted by scientists at both NREL and Oxford PV, and in the process, I was, of course, left with even more questions. I wanted to experiment with many concepts, one of which was lead-free perovskites and their effect on the environment. However, I understand that I haven't even scratched the surface of the science behind solar cells, and I'll need years more of education to get to a point where I can conduct experiments with others. I began the TSS program in 2019 with minimal interest in solar technology, but now it's central to my future. I wanted to become a scientist that works with anything biology related for as long as I can remember, but I didn't realize that that could have anything to do with solar technology. Currently, I hope to study bioengineering in college and use my education to work towards improving solar cells. I'm incredibly grateful to have this opportunity to share my research and passion with others, and I hope that the TSS programs can inspire other students like me to explore the field of solar technology and what it offers. Thank you to everyone who is watching and to everyone who helped me to get here.